Welcome to gases and temperature for chemistry, okay? We're going to learn what temperature is, and we're going to talk about it in terms of gases. We're also going to introduce the idea of pressure and some words that go along with that, and where measurements of pressure kind of came from. So hopefully by the end of this, you'll be able to figure out why this hot air balloon is rising. The word wall terms that we want you to be familiar with, and hopefully we'll be more familiar with at the end of this unit, are volume, temperature, moles, absolute zero, should be a new word, Celsius, Fahrenheit, and Kelvin. They're people that did discoveries in temperature, and we actually have units now named after them, so they might sound familiar. Great. Let's see how we get to... There we go. Characteristics of gases. Gases collide with each other, and that's why they push each other out. They spread out. When you take this gas out of the container, they diffuse, also called effusion. And you might remember, if you take the lid off of a perfume bottle, you don't have to do anything. Eventually, the room's going to get a whole bunch of perfume molecules that will spread because you'll be able to smell them. So if you if you spray something at one end of a classroom, eventually the whole class will be able to smell it, for better or for worse. Okay, that's because they have random motion. So the motion of gas molecules is they collide with each other, and they're randomly colliding, so eventually they all kind of spread to the far corners of their container. This is because they don't actually have an attraction to each other. What makes gases gases is they don't want to stay together like solid and liquid, and or they have enough energy to overcome their attractions, and they have a lot of energy and motion, and that's why they spread out and they behave the way they behave. And think of grade schoolers on the last day of school. They just they're spread out all over the playground. They're going all over the place. So gases, bouncing off the walls, stuff like that, bouncing off each other. That's some characteristics of gases. So just to compare, to remember our three forms of matter, the major forms, solid, liquid, and gases, you can see that solids have a set volume, set shape, and they have a higher density. When you set a piece of solid on the countertop, it doesn't start melting into the countertop, okay, unless it's going to become a liquid. So the molecules have an attraction for each other, and you might say they have less energy, or comparatively, because they're still gonna move, they're gonna vibrate, but they're gonna be next to each other in a set order. Liquid, you have molecules moving around, but they have a set volume, and they hang together in that set volume, so they're gonna hang together in the bottom of your glass, and they're never gonna take up more or less, mostly. As we'll find out later, you're going to experience a little bit of these liquid molecules. They might separate from each other if you give them more energy, more heat energy. But the density is higher. Now gases, they're so spread out, as you can see a little gases icon right there, that their density is much lower. They don't act like they have an attraction for each other. Really, some gases they do, but they just don't mostly act like it, okay? So the volume of the gases is going to be whatever container you put them in, and same with the shape, okay? So focusing on gases, and now temperature. So temperature is a measure of kinetic energy. So molecules have energy of motion, just sitting there. They have energy. Even if it's as a solid, they're vibrating. As a liquid, they have more energy, enough energy to overcome attraction. So you can melt something from solid to liquid by adding heat here, as we've shown. Also, you can give enough heat to make this liquid turn into gas. That happens when you boil water. So two things could occur. Of course, the number of collisions is going to increase because the kinetic energy of the gases, since they're free to move around, they're really going to move around, okay? Enough that they're going to spread out as far as they can. So first of all, they'll spread out. If they're in a container and the volume is still set within that container, those gas molecules are just going to bounce back and forth and have more collisions. So more heat means higher temperature, higher kinetic energy of motion, okay? And we're going to talk about temperature. All matter then has a measure of energy, okay? Or it wouldn't be matter at all. So where's energy? That energy is in its bonds between atoms and in the atoms themselves and the particles themselves. So to kind of exemplify that, energy, E equals mc squared. Energy is mass times the speed of light squared. That's what that little c is. So that's Einstein's theory, and how he came up with that equation is super complicated. But yeah, energy, matter is just a form of energy. Okay? And kinetic energy is one type of form of energy, and light energy is another type of form of energy. So what we're trying to say is everything has temperature. Okay? But how do you show that temperature? How do you show it in a quantity? How do you show it in amount? And what scale do you use? Well, we are lucky to have the invention of the thermometer. It was actually Galileo that came up with kind of a rudimentary water thermometer. You may see on some people's desks. They're kind of cool with little floating things. So he came up with the idea. Then we had people like Fahrenheit pick up this idea, and they put liquid in a tube, and they found out that increasing the heat of liquid in a closed area is going to add enough kinetic energy that liquid is going to take up more space. It's going to have more volume, and it rises up through this little thermometer, through this tube, yeah. And then if you make little marks, you can say, okay, I've added this quantity and this quantity and this quantity. So they called those degrees, so that you could mark the degrees, and they have the same distance between the lines, and then you can compare how hot or how much more temperature something has and more heat energy than another. So heating, remember, liquid travels up, cooling makes the liquid kind of condense in there, okay? It's just with gases, it's just so much more pronounced because they expand a lot more. We'll talk about that more later. Temperature is a measure of energy. Okay, so ways that we depict the temperature as a quantity. Mr. Fahrenheit came up with a Fahrenheit scale, and what he put as 0 was just the lowest temperature that they were able to create in their labs back in the 1700s. They would take ice and salt, they'd force a phase change, and when you force a phase change like that and the salt interrupts the bonds between the water molecules, then you're actually going to be taking heat energy to do this phase change, and they're able to get it colder. That's why we use salt when we're making ice cream. It lowers the temperature so you can get that ice cream really cold and turn it into ice cream. 100 Fahrenheit was actually close to body temperature. Well, right now we know it's probably more than about 98.3, but some people are 99. Body temperature can be arranged, but that's okay. So that's what he based his scale on. Celsius decided to kind of standardize it with 0 being the freezing temperature of pure water, and 100 is boiling. And we'll talk about this more later, but that has to be at sea level. If you're camping and you're boiling water, it's not getting as hot. Just saying, your food's not cooking as quickly because the water is escaping if it's boiling. But the coldest recorded natural temperatures on Earth happened in Antarctica with negative 89.2. We still, that would be negative 128.6 in Fahrenheit. We still have negative numbers. So even though you have a temperature of 0 in Celsius and Fahrenheit, it doesn't mean there's no energy left, okay? That's cold. So how cold can something get? Lord Kelvin calculated that to have no energy left, the temperature would have to be negative 273 degrees Celsius, okay? And something hugely negative in Fahrenheit. I don't know off the top of my head. He decided to call that absolute 0. That's the theoretical temperature where there's absolutely no heat energy in those molecules. No energy. Remember I always said that all matter has energy? So the theory is the matter will cease to exist if you don't have any more energy left. But it's theoretical, okay? We cannot actually reach absolute 0 because it takes energy to take heat out. So we're able to get really close, actually, in laboratories on Earth now, but it's probably not going to be reached, and then everything would cease to exist. So who knows? We don't know. The matter would cease to be matter, I guess. So we're saying when performing calculations with gases, it's very important to use Kelvin for temperature, okay? Or Lord Kelvin will come and smite thee. Okay, so temperature is a measure of energy. We just talked about that. Oh, here, I went back. Sorry. All right, here we go. Always use absolute temperature when calculating with gases, right? I can't emphasize that enough. If you don't, Lord Kelvin will come and smite thee with his sword, okay? Also, the calculations won't work out because you can't have negative numbers. You just need zero energy to be zero. You need to start the scale on zero. So Kelvin was right. He was trying to do gas measurements and gas calculations, and it had to be zero as zero energy. So we kind of just comparatively, it's negative 459 at Fahrenheit, and that would be zero for Kelvin. So the weird part is the Kelvin scale is actually loosely based off of the degrees of Celsius. So they line up, as you can kind of see in the corner here. Maybe it's cut off a little. Kelvin is whatever degrees Celsius adding 273 because we have to add the fact that there is a lot more energy at 0 degrees Celsius. But you can kind of see that on our little chart up here. For Fahrenheit, though, because Fahrenheit and Celsius, they don't line up with 0 being no energy. They're totally different. They're a totally different scale. And so you got to do Fahrenheit minus 32 degrees. And then 5/9 of that, and that'll convert to Celsius, okay? So we're going to do a little bit of math with that equation, okay? Here we go. So convert the following. All right, so we just need to use these equations, okay? So hopefully you kind of remember them a little bit, and I'll review you. All right, so 75 degrees Fahrenheit. You put that in the Fahrenheit equation. All right, remember it was 5/9 times that 75 minus 32. Okay. Remember, you do the parentheses first, and then you can multiply by 5 and divide by 9, or divide by 9 and multiply by 5. That's okay. Then what we're going to get should get 59 degrees, or 57, sorry, degrees. And that's in Celsius, because if you've converted it, now you're in degrees Celsius. To do Celsius to Kelvin, that's a lot easier, because Kelvin is the Celsius plus 273. That's it. So all the Kelvin measurements are going to be 273 degrees more than the Celsius. And that's it. And that's in Kelvin. We don't say degrees Kelvin for some reason. We just say K for Kelvin. All right, cool. So Kelvin to Celsius, that's 4. So, you like doing your little equations. Kelvin equals 100 plus 273, or you can realize that you're going to be ending up taking 4 minus 273. Let me subtract 273. I said 100. That's supposed to be Celsius right there. See, shy guys. There we go. I'm just going to do that. Okay, so we're going to get negative 269. When you take 4 minus 273, yeah, you're going to get a really low number. Because 4 degrees Kelvin is really close to absolute 0. Okay, can you see that? 269 is what you should get. My first time using this pen. Crazy. All right. Let's try Celsius to Fahrenheit, okay? You can do where you started out with 75, in that equation we kind of had used above, and then go for 5/9 of whatever Fahrenheit is. We don't know. We put an X for Fahrenheit. Okay. Minus 32. And then order of operations, we're going to multiply by the reciprocal. So it's 9/5 times both sides, which should be 1 here. And then you're going to take 75 times 9 divided by 5. And then we're going to add 32 because you had to add 32 to both sides. Okay, to get rid of that. So X, which is a Fahrenheit, equals all that. See if you can put that into your calculator and try it. You might want to pause the video and try it to make sure that you're getting the right answers. Or later on, try it. Okay, I get 167. All right, degrees Fahrenheit. Super cool. Actually, it's not very super cool. It's really hot. It's burning. I would not recommend that. You'd be burning it. Okay. So next, let's see what we can do here. So that's how to do the temperature conversions. We're going to talk about pressure and standard temperature and pressure. So that's kind of our word wall terms. If you didn't know by now, when you're heating gases, they expand, which makes them less dense. So you can see a hot air balloon's not really being held up by anything. It's floating because things that are less dense float. So the air inside the hot air balloon is less dense than the atmosphere around it. And of course, if they stop adding heat, eventually the air is going to cool, or at least going to get to the level where it's the same temperature as the air around it. And it's going to create that, it's going to go to buoyancy, and you won't fly into the upper atmosphere, hopefully. Yeah, you don't want that. So yeah, we're going to talk about pressure and area and force as well. So pressure is force per area. And remember, area is a smooth, two-dimensional amount of area. It's not three-dimensional. Okay, it's not like volume. All right, but so force per area. So some of the temperature or pressure measurements could be pounds per square inch. Okay, PSI. And we're saying it's a force per area. So if you increase the amount of area, then you're gonna get a smaller number. It's gonna be a smaller fraction, right? If you decrease the surface area, then this pressure is gonna be bigger. So which shoes would you prefer on walking on snow, where you want to like spread your pressure out so that you don't fall right down? Yeah, you probably want to use the snowshoes for snow, but the shoes that exert the most pressure per area is going to be your high heels, right? Don't want someone to walk all over you with those, okay? Here we go. Oh, so here's a toughie. Do you prefer a bed of nails, lying on a bed of nails, or standing on this little, I don't know how big that would be, thing of nails? Increasing the surface area, so you notice the bed of nails is increased, like it's over a larger area. It's going to decrease that force, isn't it? So you can actually have less pressure exerted on your skin, and it's not enough pressure to poke you with the nails. I've heard these actually kind of feel kind of good. Weird. I don't know. Decreasing surface area, then it's going to increase force, and the overall pressure will be more. So you will go right in. If you did this, if you stepped on that little dealy bobber smaller with all the little nails, it will go through your shoes probably. You know, hopefully you're doing that with your shoes. Okay. So yay, we do prefer a bed of nails. So pressure. This guy named Torricelli, Evangelista. Ah, yeah, he's Italian. He actually studied under Galileo, and he developed this principle that pressure, of air pressure, really, too. Pressure in general, but air pressure. And his quote was, "We live submerged at the bottom of an ocean of air." Isn't that awesome? It's kind of poetic, too. Okay, so, but what you had to do, same kind of idea of the temperature, but you had to have one area open to the air. Okay, so you can see that the mercury barometer, they call that pressure measuring gauge, it's going to be open, and it's going to allow whatever air pressure and gas molecules that they're colliding at. They collide at the same rate if they're at the same temperature, by the way. I don't know if we talked about that. And they're going to push down that liquid at a certain pressure, okay? And then that's going to cause the mercury to rise. And we just put a bunch of degrees in here. And since Torricelli discovered that, we like to call it the torr, okay? So 1 millimeters of mercury being raised up is 1 torr. This guy on your right is kind of fun because you can put your hands on it, and if you heat the air that's in the bulb, it's going to expand the air, it's going to push the liquid back out, but it's also open to the open air, so maybe that's closer to what Torricelli kind of played around with. Also, if you go into the upper atmosphere, if you climb a mountain, you actually have less air on top of you. I mean, not only are your worries and cares less and you feel lighter maybe because you're camping and having a vacation, you're in the outdoors, but, you know, you actually have less air. Literally, you have less pressure on you. And so it would actually suck some of this liquid out of the vacuum in here. So your barometric pressure would be less, would be measured as less. I don't know if you've heard, but sometimes if you get a lower air pressure, might be because the temperature has dropped, but that might allow air pressure of a storm to get sucked in, or winds to get sucked in. Air is going to come in, it's going to move. So if you're into weather and predicting weather, that's kind of part of it. They say when the barometric pressure drops. So cool. So yeah, we're surrounded by an ocean of air, and if you're feeling a lot of pressure on you, it's probably because we're at sea level, and yeah, it's the air on top of you. Okay, and it's around you, still bouncing around in your head. The manometer is just a way to kind of, instead of connecting to the open air, you connect to a gas sample, and then the gases are gonna, in that sample, are gonna collide at a certain rate, and they're gonna have a certain pressure, and then that pressure will push down on the liquid and will push up the other side, and then you can measure air pressure. And some guy's using a ruler. He kind of made a homemade one on the right here. That's kind of cool. So just pushes down liquid, and then yeah, you'll see how you can compare gas pressures. Okay. So what are we gonna do with this? All right. Well, we did notice that at sea level, you have a certain amount of air pressure. So we try to standardize it as something, One standard is freezing for fresh water, and so it's 0 degrees Celsius. And then the other one could be at sea level. So we decided that air pressure at sea level, what is that pressure? We're actually going to make it 1 atmosphere. Okay, so that became a measurement here. On Mr. Torricelli's mercury barometer, it was 760 millimeters mercury, or 760 torr high. So that's where that number came from. If you're at sea level and it's freezing, okay? So we call that a certain thing. Also, at pounds per square inch, it's 14.7. That's already kind of a physics sort of measurement here. And kilopascals is how many newtons of force per meter squared. So a newton meter squared, kilopascals is what we decided to call that. Pascals is probably dealing with centimeters instead of meters, but yeah, it's kilo because it's meters. So we like to use that though because it's close to 100, and it makes calculations nice. The nice thing is that at 0 pressure, all of these are 0. Okay, because yeah, there's no pressure, so they're all standardized for 0 pressure is 0 ATMs, atmospheres, 0 millimeters of mercury high, way at the bottom, and 0 pressure per square inch because there's no pressure. So they're all standardized, they're all proportional. So it makes the calculations kind of easy. Okay, so we call this air pressure at 1 ATM, 760 millimeters mercury, or torr, 14.7 psi, 101.325 kilopascals at the ocean sea level at 0 degrees at standard temperature and pressure. Okay, so what that enables us to do is make proportions, and we can use those equivalents or proportions at STP to convert these. So now we can convert these measurements. We want to know how many torr is 2.5 atmospheres. Okay, so there's 2 ways to do conversions. However you like to do them is great. One is unit analysis, and the other one is the equations. Okay, so if you're an equation fan, and you guys are super awesome at doing these equations and at solving them, that's awesome. You can just do it this way. You can say, okay, so 2.5 ATMs is as to, I don't know how many torrs, not yet, we're getting there, and put that equivalent to what it is at standard temperature and pressure. Well, at standard temperature and pressure, it's 1 ATMs, and remember in torrs, it was 760. Ooh, okay. So put 760 on the bottom. It's okay if you want to use torrs. Yeah, if you use millimeter mercury, as long as you don't get confused, okay? Remember that in that case, you have equal sign, and so both of the units on top need to match, and both the units on the bottom need to be equal. Do your cross multiplication thing, or multiply by the reciprocal, however you learned it. That works for you. So you get 760 times 1 ATMs, okay? That's awesome. The other way that you could do it is by doing unit analysis and saying, okay, I'm going to multiply by my conversion factor, which is the fact that I don't know how many torrs, 760 torrs, my bad. We find out 760 torrs is as to 1 ATM. So going to cross units out. ATMs on top and bottom cross out. So you get 2.5 times 760. It's the same calculation. Okay. I get, what do I get? Oh, 1900 or 1900. Yeah. Torr. It should be a big number, right? Because there's a lot of torrs at sea level on standard temperature pressure. Okay. Cool. Okay, so however you like doing it is great. I find the unit analysis is super easy for me. Remember, you're just doing proportions, but unit cancellation, it works, and it's fun. Okay, it's so 101.325. Some people leave off the 0.325. I don't know why. I don't, just being really super precise, I guess, as to 760 torr. So you're going to multiply by 760, the 98 by 760, and divide by the 101.325. I get 735 torr. Okay, correct me if I'm wrong here, if I get this wrong. PSI, you got 12.3. Want to find out how many ATMs that is? Well, one ATM is 14.7 PSI, so it's going to be less than one ATMs, because 14.7 PSI is one ATM. So you're going to end up taking 12.3 divided by 14.7. I get 0.837. And yeah, I left 3 digits there. Oh, that was weird. 0.837 because we had three significant figures there. So that's how that works. And of course, you do want to put your units down, because like, what did I calculate? I don't know. Yeah, you got ATMs because PSIs canceled out. Okay, so the 780 milligrams of mercury to ATMs. One ATM is 760 millimeters of mercury. Okay. All right. So then 780 divides by 760, and I get 1.03, which makes sense because 760 is one ATM, but that's a little more than 760, and we're talking ATMs. All right. So hopefully that you get comfortable converting, and that's all that we're going to do for the temperature in this class. And then we're going to talk about gas laws. Just remember, standard temperature and pressure. Here's the thing about gases, though, that you do need to know. Gases spread out in a predictable fashion. We call that like the ideal gas law. We have a we can find information we'll talk about more later, but at 1 atmosphere pressure and 0 degrees Celsius, that's 273 degrees Kelvin, 1 mole of gas always occupies about 22.4 liters. So, I mean, in that screen, that'd be like this much in my screen, proportional to me, what you're seeing, if you were me, okay? That's how many liters of gas that the gas wants to, the volume that the gas would like to take up at 1 atmosphere pressure outside of that container, and if the gas is at freezing, and there's only 1 mole, so there's only 6.02 times 10 to the 23rd particles of that gas. So that's something that you can use to calculate how many moles of gas that you have. If you know the volume and it's at center temperature and pressure, you could use that conversion. Now later we're going to find out that if the temperature is different or the pressure is different, gases generally behave in a pretty standard fashion. There's some exceptions, but we can predict how much gas that you have, or we can predict other variables if we know some of this information. So we can do stoichiometry with it, is what I'm trying to say here. If we have 3.2 liters of gas consumed in this equation, how many moles of magnesium were burned in the first place? Because we can find out how many moles of oxygen that 3.2 liters was, okay? So let's just take the fact that, this has to be at STP, standard temperature and pressure, okay? Because we don't have any other information. We don't have what the actual temperature was and the pressure, so it should say at STP. Okay, so let's find out how many moles that is. 3.2 liters. And we don't know how many moles. But we do know that at this temperature and pressure, 22.4 liters should be 1 mole. Okay, so we can do the equation like that. You can also do unit analysis, like we did before, where you just cancel out the units. That's fine. Cross multiply, we get 2, and you put the 22.4 here, or you're multiplying by the reciprocal, and everything cancels out. So we do 3.2 divided by 22.4. All right, and that's 0.14 moles. Okay, that's how many moles of O2. And you know it's a 2-to-1 ratio of moles of oxygen to moles of magnesium. So you can just double that, and then that's how many moles of magnesium burned. Okay, so we got this O2, that's how many O2, and then 1 O2 is 2 magnesium moles. Remember that. Sorry, it's kind of sloppy. I don't know. So we get let's do 0.29. Yeah, 0.29. Okay, so that's how many moles of magnesium. How many grams of magnesium is it? Ah, man, we gotta know how many grams per mole magnesium is. And for that, I need my periodic table, but I loaned it to my son. Okay, so molar mass of magnesium. Looking that up. So we're going to start with what we have. We have 0.29 moles. We could have done this all in one shot. All right. Now, if you want, you can use equations too. Moles is 2 grams, as moles is 2 grams. But if you're doing unit analysis, 1 mole of magnesium is going to be 24.3. Oh, goodness. Okay, so you get 0.29 times 24.3. Did that kind of 2 different ways, but oh well. I get about 6.94 or 6.9 because we only have 2 digits, 2 significant figures. So 6.9, oh geez, I'm thinking grams, so I wrote a G. Okay. Hopefully you can remember that's how you're going to do using the fact that at standard temperature and pressure, 1 mole of gas is 22.4 liters. Okay, so I'll have an assignment that goes along with that, and then we're going to hopefully get a little farther this week with the gas laws of pressure, volume, and temperature not being at STP, and maybe not having just 1 mole, or maybe you're going to change the number of moles. So things are going to change when you're dealing with gases, and you can predict them because of the ideal gas law, and it kind of just says gases don't have any attraction for each other. We all know that reality is a little different than what's ideal, but we can zig and zag, and we can say in generic terms this is what's going to happen and how gases behave. Anyway, thank you very much for following along. I hope that was helpful. Please give me some comments that'll help me decide if I need to fix things, or if you need questions and stuff like that. That really helps get this show on the road. Okay, so hopefully I'll figure out doing it a new way. So there we go. We got this. All right. Have a good week. Talk to you soon.